Hey guys, for those online, can you hear me? I just shared my screen. Can you guys hear? Can you guys see the screen? I didn't make them. Hey guys, can you guys hear me? For those online? Okay, cool. Screen is okay? All right. All right, let's get started. Sorry I had to move this lecture from Monday to today. I was working on a proposal. I actually won that competition. I got a project. So I'm gonna start January. It's a new project. So I'm pretty excited to start a new work with Boeing on composites. So today I want to talk about design, which is some basic rule of thumb stuff. I've covered most of the material I wanted to cover in the semester, all the main topics. You know, the micromechanic failure criteria, hygrothermal stress, interlaminar stress, fatigue, things like that, buckling. So it's it's pretty wide introductions. I guess for the remaining of the course, I basically wanted to give you a final project, which is a calculation using your CLT code, and finish with that. No more exams, just one more project. That's it. Unless you wanted to another exam, I'm yeah. Give me some feedback if you wanted to, what you think about it. So email me or something like that. What you want to do. So I want to go over today some sort of empirical design practices. One of them is from a book by Crystal Casapoglu, which is a new book. I think 2016. It's very nice engineering design sources. It has a chapter on rule of thumbs, how to design when you design a composite plates panels. I'm very impressed. So I kind of summarize that in a few slides. I want to go over that. You rarely see this kind of presentation. It only engineers who practice kind of thing for many years, they know this. So it's kind of a pretty privileged information, if you will. So the Crystal is doing this kind of work for many years. He's MIT graduate working in the composite industry. So his presentation are very nice. So I want to go through maybe 15, 16 slides on those general rules when you design an actual plates. And then I'm going to go over a numerical example, which is actually came from Kaush's book, chapter 5. There are some design examples. I picked one on drive shaft. So we go through how the problem is abstracted into a CLT problem, how it's solved, how it's trade-off study, all those things. Okay. So that's general plan. This is I believe this is a last lecture. We're gonna introduce new material. The next lecture, we're gonna go over the final project. What I want you to do on Friday. And then the remaining lecture will be on need basis. If you need more lecture, we'll have lecture. If you don't, we can do individual Q&As and things like that. So that's my plan. Okay, let's get started with this. Next page, full screen. All right. So these are good design practices or rules of thumb for engineers who work on this. I came summarized by engineers who work on this kind of a business. Number one, it's simple to understand. We learn these things from our CLT practice. The layout of a laminate should be symmetric. That should be your first priority. So when you design anything, try to make the laminate symmetric. Okay. Eliminates unwanted in-plane membrane strain and bend coupling. So your B matrix is 0. All right, that's rule number one. Sometimes you have to do trade-off. Sometimes it's not totally avoidable. You have to have some coupling, that's fine, but you want to minimize it. The second rule is that the layout should be balanced, meaning for every plus Z apply, there should be a minus Z apply. So if you do this, what you have is you eliminate extension shear coupling. Okay. Unless you intentionally want this. Most time people don't want this. Okay. If you do this symmetric, balanced, then you don't have those couplings. Number 3 is the keep bend twisting coupling under control. You either zero it out or minimize it. If you use anti-symmetric laminates, your D matrix, D16, D26 are automatic 0, but that violates the first rule. First rule, you want a symmetric. Okay. So you can compromise to make a design which is, you know, almost anti-symmetric, but not quite. And then so you can strive to make this two numbers small instead of absolute 0. If you use a woven fabric, a UD material only in the 090 plies, you make this cross plies, your D16, D26 will automatically be 0. So that's one option you can do. 10% rule. This is an interesting rule. When you design a laminate, let's say if it, with a 60 plies, 100 plies, it's not uncommon to have a thick laminate which is hundreds of plies. Okay. So this rule says you want to have at least 10% of fibers in 0-degree direction, in 45 direction, in minus 45 direction, in 90 direction, 90-degree direction. 0 being 090 and being the principal directions. So basically, that'll take up 40% of your plies. So with this plies in these 4 directions, you cover your bases. This is so that if you, let's say if your primary load is 0 directions, okay, you design to carry your major design loading, which is huge load, you want to carry that, but you don't want to align all the fiber in those directions. You separate out some other plies to make it go these 4 directions. This will cover up in case you have a secondary load. You have some situation that you run into situation they are loading those directions. You don't give up to make those directions extremely weak. So with this kind of practice, you have all your base covered. Okay. So when you have a secondary load, which not in the primary direction, your panel is still strong enough to cover those. So that's 10%. Some of the 10% is boosted up to like 12%. So you put a 10% in 0 direction, or 12% in 45, 12% minus 45, and 12% in 90. And then the remaining plies are in the primary loading direction. Okay. So that makes the panel well-rounded instead of extremely strong one direction. In other direction are very, very weak. This is sort of a kind of compromise. Okay, that's called 10% rule. All right. This is a this is about sequence. When you have a UD ply, let's say you want to build up thickness, it needs like a 10 UD plies. You don't make the 10 UD plies in the one direction next to each other. In that case, if one UD ply had cracked up, the crack actually can easily propagate to other plies. So when you have a plies, which is exactly the same orientation, UD plies, it doesn't have a resistance for the matrix crack to go through the layers. Let's say you have 100 plies all in the same direction. The matrix crack gonna go all the way through them. Okay. So avoid stacking up those material next to each other. You put a, let's say you have many 0 plies, you put a couple 0 and put a couple 90s in between. That kind of limits the extent of your matrix crack propagation. Okay. Is this understandable? All right, so we have a few people coming a little late. We just talk about the plans for the semester. Let me say one more time. So we're gonna finish today's lecture on some empirical design rules for laminates and one example. Then on Friday I'm gonna give you the design project. What I want you to do as the last exercise on your using your CLT code. And then that's pretty much all the material on the cover for the semester. For the remaining time, we're gonna schedule on a need basis. Let's say you wanted to ask questions about your code and things like that. We can schedule and based on the need. I don't plan to give another exam for this course. The remaining thing will be the final project. Okay, if you have source and questions, concerns, send me email. I'll try to address those. Okay. All right. So this rule number 5, do not put many UD plies in the same orientation next to each other. Okay. Number 6. All right. Let's say if you have a 1D structure and then the bending is a critical aspect. In this case, you want to place 0 degree plies as far away from neutral axis as possible. So that way the contribution to the bending stiffness is maximized. All right, this is, I believe, if you understand solids, this is pretty understandable. Put 0 degree plies as far from neutral axis as possible. This is when you want a beam-like structure, 1D structure with high bending stiffness. I mean, if that's not a requirement, doesn't matter. If bending is a pretty important factor of design, you do this. This give you the benefit of using the same amount of material but achieve higher bending stiffness. Put plus minus 45 plies. This is about buckling. Put plus minus 45 plies as far away from neutral axis as possible for the purpose of improved buckling resistance. The plus minus 45 help resisting buckling or crippling. Imagine a thin panel that you put in a shear or transverse loading. It tend to buckle. And buckle forms a out of plane motion in the plus minus 45 directions. So if you place plus minus 45 plies as far away from neutral axis, your panel will have a higher resistance to this kind of deformation. So the effect of this is actually increase D66, which improve the crippling and buckling resistance. Okay. Frequently, composites are joined by fasteners. If you never heard of this, the fastener is pretty universal. The other alternative is a bonding adhesive joints. But buckling is pretty reliable, strong joints. Sometimes preferred over adhesion. one of the sidetrack. Let me talk about this corrosion issues. I guess you do not basically want to have aluminum in contact with graphite material directly for the purpose of corrosion resistance. There is a phenomena called a galvanic corrosion. So how many people have heard this galvanic corrosion between aluminum and graphite? So the material has different level of nobleness. If you, this is one way to capture the corrosion potential of a material. For example, precious metal, gold and platinum, silver, those are we call noble metals. And then zinc, lead, iron, those are less noble. When you put a noble metal together in contact with less noble material, the less noble material is corroded in accelerated fashion. When you put them in contact, electrical contact, okay. It turns out the graphite is pretty noble material. Graphite, I think, on the noble scale in electrochemistry, is higher than most metals. So what happens when you have a graphite material directly in contact with the aluminum corrodes very, very fast. Okay, you have things got wet at the joints. You have a accelerated aluminum corrosion. So it's not acceptable. You're not gonna have a durability. Okay, so it turns out that a lot of the fasteners are, for that matter, steel is not very good either. So for those who had worked with Boeing, you probably know that all the fastener on Boeing 787 is made of a material called titanium. There's a good reason for it. The number one reason for using titanium is corrosion resistance. Because you don't want to put, titanium is a semi-noble metal. It has less of corrosion issue than aluminum and steel, okay? And the downside of using titanium is super expensive compared to those. It's very expensive parts, hardware, okay? So that's a trade-off. For durability, you use a titanium fasteners. These rules that we're going to talk about, I guess maybe three or four rules on fasteners. Has nothing to do with corrosion. Yeah, it has only something to do with the mechanical strength. This rule number one is that you want to have a pretty so your skin thickness to fastener diameter ratio should be less than 1/3. So you want your diameter to be pretty high in diameter to avoid the diameter is bending by itself. When you have a shear loading or pure loading, if the diameter is not thin enough, your diameter, your fastener tend to bend. So if you make that thick and you clamp it down, you pre-torque it down, you put some force, you actually apply a pretty uniform compression along the free edge. That's what you want to achieve. What you don't want to achieve is using a diameter which is very small diameter. Under loading, that fastener itself will bend a curve, which you lose, which cause you lose compression on one side, things like that. So this rule number one, you want to make the diameter of the fastener big compared to the thickness. Okay. All right. Rule number two, this is relevant to a lot of aerospace structures because they use a countersunk fasteners to have a smooth surface. The countersunk depths need to be so you basically you want to have skin thickness, which is the total skin thickness to countersunk depths greater than 1.5 to avoid pulling through the fasteners, pulling the fasteners through the skin. Okay. All right, so you don't want it to, so you want to have this, the amount of material engaged in the countersunk part big enough. And the remaining thickness of the material without the countersunk feature thick enough to avoid this material being pulled through. This is rule number 2, fastener rule number 2. 45-degree fabric plies on the outside. Low speed impact is one of the major failure modes, at least one of the major concerns for composites. If you use fabric are the woven stuff. They have they hold themselves better. They tend not to fray because they're interlocked in a way. They're interlocked. So if you put this on the skin layer, even if you have some impact, you have less likely to have a fiber splitting on the outer and on the top and bottom surface. So this kind of improve the damage resistance due to low speed impact. When you make the a fabric layer on the outer side. For a panel, you want to have plus minus 45 degrees on the outer surface, especially when this panel is a stiffener or web, supporting web, a stiffener in a thin wall structure. This is because very frequently those stiffener or web are loaded under shear. When you have this plus minus 45-degree plies in there, it kind of have give you a high shear resistance. Resist shear load better. All right, this rule number 3 for fastener is that if you have, let's say, a log, a hole, and you join those fasteners, you do not want this log to have a kind of zero. Let me draw a picture of this. I think better to show a picture. Let me see this. All right. Let's say this is a log. Let me get it. Let's say this is a blade of helicopter. This is a hole that actually joins to the whatever the holding structure is. There's a pin that connects them, right? Now let's say this is a composite panel. You don't want the layout to be. Let me give you a worst layout. The worst layout is all zeros. Okay. You guys see the lines I draw? So what happened in this case is this material, because the interface it tend to be sheared out easily. It's not a strong joint. And you don't want the direction to be this direction either. So the best case for the fastener, when you have a fastener, this kind of joint, is to have this fiber in the plus minus 45 directions. This is a good choice. And then you dig a hole, and this kind of fiber orientation can hold it together. That's what this rule about. Okay. I hope that helps explains it. All right. Stop me if you have questions or comments. There's fastener rule number 4 is the spacing. It's a spacing requirement. The space between fasteners should be big enough. So you don't want a fastener to be too close. Fastener itself introduce stress concentration. When you put them in a dense manner, very close, they tend to form a potential path for crack to coalesce and tear through. So you want to keep the fastener spacing spaced out. You don't want to fastener one diameter apart, hundreds in a row. That's like a pre-crack. You're basically inviting the thing to fracture from there. So as a rule of thumb, the fasteners should be 4 to 5D apart. So if the diameter, let's say, is a 1/4 inch, you want to put 4 times 1/4 inch in between the holes. You space them out. So you have less hole-to-hole interactions, and you decrease stress concentration effect. Okay. And fastener rule number 5 is the distance between the fastener hole to the free edge, and you want to maintain a good distance so that it doesn't push through in that direction. That is half a D, 2.5 diameter plus a little bit of a extra space. That's the rule of thumb for the distance. Ply drop. Ply drop is used when you want to design a material with a thickness transition from a thicker part to thinner part. This is frequently done in the blades, in the turbine blades, in the fan blade. Near the hub, the ply is thicker, and then as you move toward the tip, the ply is thinner. You can achieve this by something called a ply drop. Ply drop is that you basically lay up ply of different lengths. Near the roots where you want high thickness, there are higher number of plies, and then you drop certain ply at a certain distance. So this is a good picture of ply drop. So this is to create a transition from a panel high thickness to smaller thickness. You basically drop plies. Okay. And this set of rules basically is a very good guideline for how do you arrange how ply is dropped. So number 1, avoid external ply drop, which is external ply drop is basically you don't want the free edge of the ply exposed. Let me draw an external ply drop. Let's see if you can see this. External ply drop is, so let's say I want to make a transition from this is the external ply drop because the free drop is on the outer surface. This is to be avoided. You never want an external fly drop. You want a fly drop to be covered by a layer. This layer covered up. You don't want a fly drop and the free surface to be exposed at the steps. So that's rule number 1. External ply drop is to be avoided. For more than one ply drop, try drop plies symmetrically, not lies, plies. That's a typo. For more than one ply drop, try drop ply symmetrically. That means you drop from either side. And this picture here, the top picture, this one, is a very good example of a symmetric ply drop. See, you drop from, if you look at the midplane, the upper half, lower half is symmetric. You drop from either side to get you the desired thickness reduction. And that's a good design. Drop symmetrically. Rule number 3, ply drop guidelines is avoid dropping more than 0.5 millimeter worth of plies at the same location. So you don't want to drop a huge amount at one location. You spread it out. This picture here, right here, where my cursor flying on, that is a huge drop at the same location. And you create a huge pocket inside, which is bad. You don't want to stagger them. You don't want to, at the one location has huge vertical drop, okay? The distance between successive ply drops should be at least 10 to 15 times the drop height. Let's say if you want to drop vertically 1 millimeter, you want to drop thickness, and you don't want to do it in successive fashion, and the distance need to be 10 to 15 times the amount you want to drop. If it's a 0.5 millimeter drop, you want to be 5 millimeter spaced out. Okay. This is basically so this D here, that D is the successive distance between ply drop. D should be 15 times the thickness. You drop a little bit, you drop a H is the vertical drop you have by removing a ply, and then the next drop should be 15 H time away. So this is spread out. Okay. All right, we're very close to the end of it. And this is anti-peel fasteners. Anti-peel fastener is to place fasteners when you have a stiffener used to reinforcing a panel. It's strongly recommended at the four corners. This two and this is at the one side and the other side. The four corners, you put in fasteners at those locations to avoid the stiffener from peeling out. Under certain loaded conditions, the stiffener tend to peel off of the panel. Then you lose all your reinforcing effect. So this kind of design is very beneficial. So it guaranteed that the far corner will not peel out from your panel. That's called anti-peel fasteners. Okay. So these are there are actually more rules. I only covered a few. There are maybe 10 more rules there about exactly how you design a stiffened thin wall panel, how the stiffener are arranged, things like that. In the Crystal's book, you can, if you're interested, you can look in the detail. So I didn't cover those because we didn't talk about stiffened thin wall panel. So that's a little bit out of context. So I picked the first 16 of those. I think it's universal applied in most composite structures. So I've gone through these. It's very nice rule of thumb. So when you actually got a chance to do some design, keep this in mind. All right, next I'm gonna do is basically look into an example with some sort of a real application background, which is a study of replacing the drive shaft. This is from the course book, chapter 5. I guess section 5.5. There are more detail in there. You can, if you're interested in looking those backgrounds. So it is about a component level design. I mean, the objective is just replacing the metal drive shaft with a composite one. So metal drive shaft is universal. Most of the cars, trucks, especially those driven by the four-wheel drive or rear-wheel drive, has a drive shaft going to the back wheels. Those are pretty long and pretty heavy. Usually made of a steel pipe. Okay. All right. So there is alternative. Instead of making out of steel pipe, you can make those pipe out of the composites. You can make a composite thin wall tubes, and then you close it with some metal adapters. glue or fasten it with the metal adapters, and then you can use this thing to transmit the torque through the powertrain. So the main advantage is the weight saving. Now there is overall a huge driving force to so-called light weighting, reduce weight of vehicles across the board in all kinds of automotive sectors. There's a huge driving force for reduce the weight, and for obvious reason, for reduce the fuel consumption. The lighter the vehicle is, the more fuel efficient. So you can look at the truck, which is 8,000 pound. You no matter what you do, it'll burn a lot of fuel because the rolling resistant big tires. The only way you can make it a little bit of fuel efficient is you reduce the overall weight. There's actually a big push by Department of Energy to invest in technology development to make lighter vehicles. You might have seen some of the manufacturers start using, instead of metal panels, they're using composite panels. General Motor does this. There's a brand called Saturn. Saturn is famous for using lightweight plastic panels on the rear, on your bumper and the rear panels, and the front panels. There's still some metal panels, but those panels are lighter in weights, and they have advantages. They don't rust, and if you dent them, they actually bounce back. You can punch them, they cave in, and they push out. They're kind of elastic. That also can be viewed as a downside because if you push a little harder, it cracks. If it's a metal panel, they plastic yield, and you can pull it back. Body shop can really fix it if it's a metal panel. For the plastic panel, if that have heavy damage, the only way to fix this is to replace it. But the lightweight is the big advantage. If you reduce weight here and there, you cut your vehicle weight by a certain percentage, and that saves a lot of fuels. Okay. And the fatigue shaft also have better fatigue resistance. Overall, carbon fiber material are much more resistant to fatigue than metals. They also have less of a corrosion issues compared to metals. There are still galvanic corrosions. If you take care of those, you don't have graphite in contact with less noble metal. Let's say you have a spacers, so you don't have electron pass between the your graphite panel and aluminum or steels, then you have less of corrosion issues. The material itself, the graphite material itself, has very high corrosion resistance. They don't rust. Okay. And then you can make a single piece, large parts. And they have a pretty graceful failure mode instead of snap or disastrous failure mode. They broom. They basically the fiber pop loose. So this is a better than a brittle fracture. So this is starting to design this thing. So basically, first a metal shaft is designed based on the torque requirement, and then compared to a composite one. So the first part of the problem is describing all the input needed for design the metal parts. So basically, you want to first estimate the torque. It has to go onto the shaft. So you start from engine horsepower, RPM, and then you use that to calculate the torque at the transmission shaft. So the transmission, the drive shaft is running at lower RPM, so the torque is higher. And then factor in safety factor, and there's limitations. The outer diameter need to be limited by certain size to fit into the car. So and also the length is required. You have to move the power from point A to point B. That distance is 43 inches. So these are the overall requirements. And the remaining calculation are the basically solids mechanic type of calculation. You calculate the torque needed in the drive shaft. It turns out to be 700 pound-foot. You want to resist this torque. And then you also calculate the RPM of the drive shaft. So basically, what is the highest speed you need to turn the drive shaft? So a simple calculation, assume the maximum speed of the car is 100 miles an hour. To achieve 100 miles an hour, what you need is 71 turns per second. At the highest speed, you turn your drive shaft at 71 turns per second. And the reason for doing this is the vibration considerations. You do not want your natural frequencies of your shaft to be lower than this. If that's the case, then when you speed up, you will hit the resonance. Let's say your resonance frequency of the shaft, the first mode is 50 hertz. And there's a chance that when you speed up, your RPM of the shaft go from 0 to 71 hertz, you'll hit 50 hertz somewhere in the middle, and then it'll cause some discomfort, the vibration. But if your shaft have the lowest mode 1 vibration is 100 hertz, then you will never have this issue, because as you accelerate, you speed up your car, your shaft starts spinning from 0 to 71, and you're still below the resonance. So you never go into resonance, which is desirable. So basically, rough estimation, required torque, so this basically place requirement on your shaft. This is a secondary requirement. In addition to strength, the strength requirement, you need the shaft to be strong so that you can resist this torque. That torque is 755 foot-pound. And then you want a frequency to be higher than this, okay? There's sort of requirement. We'll talk about two requirements. Number one is strong enough to carry the torque. Number two is do not go into resonance with your driving RPM. And the third one is will not buckle. Buckling is another failure mode you want to check so that the shaft will not buckle. Okay, 3 failure modes. Okay, and then when you use the metals as a the material, main material, let's say aluminum or steel, and you use it, these are the equation you use. It's very simple solid equation. TR over J. You can calculate the thickness necessary for this. This is a more like aluminum, I think, and using a fairly low strength materials. 25 KSI is it's not very strong material. So with this material, metal material, and then with considering factor safety 3, you can figure out the thickness necessary. Thickness necessary is 1/16 inch. So it's pretty thin. You think about it. The shaft OD is 1.75, 1/16 inch thick. 1/16 inch thick is only a little bit over 1 millimeters, 1.5 millimeter, and that's enough to carry the torque with the factor safety 3. Okay. But this may not satisfy the other two requirements. We ought to check the other two. One is natural frequency. The other one is the buckling. It may fail the buckling because it's too thin. Just like you're twisting an empty soda can. Even though it's pretty strong, but the wall of the soda can can buckle. All right, so additional check is done. Calculating the natural frequency. This natural frequency equation is if you study the vibration, you can understand it better. But anyhow, it basically require you to factor in the Young's modulus, section property, as well as the density of the material. With all this information, you can calculate the mode 1 vibration frequency. In this case, mode 1 is 204 hertz, which is much higher than 71. So well apart. So you're never gonna drive your shaft to 204 unless you go crazy. So 100 miles an hour is 71 hertz. If you drive the shaft at 204 hertz, that means you're going 300 miles an hour. Usually, most normal people don't go that fast. So that's frequency-wise fine. And then buckling load can be calculated. These are the equation you can look up in design sources, and you can calculate the torsional buckling threshold of thin wall tubes. And this equation gives you a threshold torque that causes buckling. Okay. The critical buckling torque turned out to be, again, way higher than your 755. So it's fine. So based on this very, very rough calculation, it looks fine for metal parts. It doesn't buckle, it's strong enough, and it's frequency-wise satisfies the requirement. Okay. It may be heavier, so then you like, but looks like it's gonna work. Now the alternative is using composites. The composites is a similar process. You first start with the requirement. So you basically you can imagine the thin-walled shaft is a plate with a shear load. You can sort of unwrapping the shaft out like a piece of paper. If a tube, you cut a tube and then you unwrapping it, become a sort of flat sheets. So when the shaft under torque, it's equivalent to the flat panel under shear. It's the same load. Okay. You can actually figure out how much of shear is applied to the equivalent flat sheets. Let me draw a picture here. So torque, if you have a shaft, which is a torque applied like this, it's the same as the flat panel with shear applied like this. It's the same thing. Thin walled. So this is a more or less equivalent. Okay. So you can figure out the NXY is the shear force applied to the panel. This is a composite panel that you want to design. This is related to the torque. This is related by this equation, NXY. T time 2 pi Rm squared. And the Rm is the radii to the center thickness. Let's say this is wall thickness, the center point of the wall. Rm is that radius. This goes in here. So you can basically estimate what is the shear force you need to apply to this composite plates. The reason you want to unwrap this tube to make a plate is because then you can use your CLT code to do the calculation. You can use CLT code to solve this case, which is basically equivalent to that case. Okay, so in your CLT code, once you propose a layup, a material, you can apply this load to the code, shear, and then that review all the stresses, which will be the stress in this case. Okay. Now this is mostly done. This is only valid when you have the tube very thin wall. The wall is a thin wall usually means that the thickness is less than 1/10 of the diameter. The thickness of the wall is much less than the diameter. If the thickness of the wall is significant compared to the diameter, then you cannot do that anymore. Now let me give you another examples. Let's say you wanted to do a pressure vessel design. The pressure vessel is a cylinder shape, capped. Then you have pressure inside. You can actually also translate this into a panel problem. You imagine the panel over here. That panel is actually under two load. One is a N hoop, the other is N axial. You can relate the hoop load to the pressure here. Actual load also to the pressure here. And through a relationship, your sigma A is a P R over thickness, right? The actual stress. No, 2T. Sigma hoop is PR over T. This is the stress, a thin wall cylinder. And then your load here, the load is essentially sigma A times T. This is a sigma hoop times T. So when you have a situation, you have a pressure cylinder, you can solve that loading situation with your CLT code, which is loaded in biaxial direction. Tension, actual direction, tension in hoop direction. And this is twice the hoop direction load is twice the actual direction load, because this is a 2-time relationship. This is twice this, 2 times this. Okay, so you can actually use your code to deal with some simple cylindrical applications. Pressure vessel being one, and torsion shaft being another one. And remember, the condition is it has to be thin-walled. Okay. Any questions? See if more people sign up. Oops. Okay. All right. Next thing you can do is just propose a layup. You pick a material that you want to use. You can use a typical material properties like the one I gave you when you do your homework. Those are representative material for the class of material. And you can just propose a layup. I applied the design rules discussed earlier. You can start with somewhere. You see in this design, this is the first time this is a 1, 2, 3, 4, 5, 10 layer symmetric layup is proposed. You can see it started with a symmetric layup, which is preferred. If you can use symmetric layup, it's better than unsymmetric layup. You have less coupling. Unless coupling is what you desire. Most people don't desire dealing with the couplings. And then you can see most of the fiber is in the plus minus 45 directions, which is the principal direction for the torsion load. Now this actually violate some of the rules. What are the rules that's violated? It violated 10% rule. Remember, the 10% rule requires that you, now in the torsion case, your primary loading direction is plus minus 45. But if you recall 10% rule, you don't want to totally ignore other directions. There are secondary loads. So you could have a bending situation in the shaft, maybe small, or tension. So you want to apply additional 10% 0-degree ply, 10% 90-degree plies. It's missing from here. So this is a violate 10% rule. They only considered you place all the fiber in the 2 primary loading directions. Okay. It didn't violate the alternating rules. You don't want to put all the 40 plus 45 all together. You don't want to put a minus 45 together. You want some alternating plus minus because it reduces the crack propagating from one to the other layers. Okay. All right. Symmetric is a good choice. And then once you have this, you can basically calculate using a CRT code. And for this book, Carl's book, he named that thing promo. That's his CRT code. But you wrote your own code. This is basically your CRT code. You can use your CRT code to see how strong that thing is. What is the under this shear load? What is the stress? How does it compare to the material strength? So you can, that's your CRT code should tell you that. And what is the total thickness? This is 10 layers. So using typical ply thickness, this wall thickness is about 49 thousandths inch. It's almost like a 1 millimeter, pretty thin. So this obviously is not safe. You can add more layer to it, or you can make design changes. You apply other plies, different orientations. Or you, instead of using gloss epoxy, using carbon epoxy. All right, so remember we have 3 criteria. One is it should be strong enough. Number 2, it should be the vibration characteristic should avoid resonance with the RPM, with the highest RPM you have. And the third one is it should not buckle. Okay. So the other 2 was also calculated. The natural frequency was calculated using the property of composites. Turns out to be good enough. And the buckling load was also calculated. The buckling load, the torque that causes the thin wall tube to buckle, according to the equation, is actually very low. It's only 183 pounds. So this is not good, not gonna work. Too weak in terms of buckling resistance. Okay, so that means this layout doesn't work. Got to change it to other layouts. Either make it thicker or change a stronger material. Things. So this design failed. This layout is not acceptable design. And that book actually explored a number of designs. We just look at one of those. And then some of the design actually look good. You can see additional designs actually introduce additional 0 and 90-degree layers. So in addition to plus minus 45, some of the designs introduced 0, 90, which is basically address the 10% rule. And then you calculate the frequency as well as the buckling load. The buckling load for some of them are actually above. For example, the row number 2, you have additional 0-degree plies, additional 90-degree plies, total of 14 plies. And then you have much higher critical buckling load. And then you have a decent natural frequencies. And that could be an option for going further. There are other issues like the joint design, the fastening scheme at the ends. That's also important. But this addresses the bulk of the shaft. This mechanical analysis basically gave you an idea how safe this shaft is. And you can actually do this with a simple tool like your CLT code that you already wrote. Of course, you use a few additional equations, like a buckling equation as well as a vibration equation. And then, of course, you can explore other layouts. All the layouts started here is symmetric. You can see all of them started here is symmetric. So there is no fixed correct solution. There are many possible solutions. All you need to do is you propose your layout, you do your calculations, and you evaluate the results in terms of 3 criteria. Is it strong enough? Would it buckle? Would it vibrate? And you pick the ones obviously with probably lower cost in terms of small amount of material. Any questions? So this is a very simple example of design calculation. This kind of design usually is conducted in the preliminary design stage instead of going into detailed design. And it gave you a pretty good idea how much material you need and roughly what kind of layout is good for certain applications. Your final project will be somewhat similar to this. I'll give you some similar to this, probably a pressure vessel problem. I'll give you some requirement, pressure, size, and you pick your layout, you do a calculation, and you propose your you just do this workflow, and you came up with a design with including the material as well as the layout, and you predict the performance metric, how much does it weigh, how strong it is, what's the factor safety, and things like that. Again, it will not be something with a fixed correct answer. It's open-ended question. There are many correct answers. You just need to pick one, and you need to back it up with your calculation. All right. Any questions? Comments? Let me say the plan about this class again for those people who came in late. So this is the last lecture where I'm going to cover new materials. For the remaining lecture, I'm going to spend on explaining the final projects and basically give you the specification, what kind of problem I ask you to solve and what kind of result I want to see. And the remaining of the course is for you to finish that project. I do not intend to give you another exam anymore. The final project, in addition to the exam you had before, will be all I will use to give you a grade. Okay. There's a question here. Yes, I will explain the project this Friday. I'll give you the specification, what I need, what I want you to do, the given material information, so on and so forth on Friday. And by the way, you should be working on your CLT code to finish the last part, which is the hygrothermal stress. Once that's done, you can use that to do the final project calculations. Okay. Any other questions? So how's the progress? How many people have finished your hygrothermal function in your CLT code? Have you finished and verified? How many of you are done with that? You can raise your hand and in the chat. Connor's done. Anyone else? Question? Okay. All right. All right, you can spend some time before Friday, I guess, try to finish up. Any other questions? No more question. I'm gonna stop here. I'll let you go, and I will see you guys on Friday. Same time. Sorry, I mistyped the time. It's 3:50. We're gonna start lecture 3:50 on Friday too, not 4:50. I mistyped it. Sorry about that. All right. Thank you all. I'll see you guys on Friday. Have a good day.